Hello everybody, my name is Arie-Willem de Leeuw, and in this presentation I will tell you something about time series regression in professional road cycling. So in time series regression we consider a collection of n pairs v which have two components. So on the one hand we have the time series denoted by d of v, and on the other hand we have a target variable y of v. So the regression task is then to find the relationship between the time series and the target variable. So what it's not time series classification, in which you try to classify a certain time series. So you try to find of a given time series to which category it belongs. And it's also not equal to forecasting, in which you try to predict the next value of a given time series. You can take different approaches to tackle this regression task, but here we use an aggregation-based feature construction approach, in which we transform the time series into certain features and then try to find the relationship between those features and the target variable. Of course, there are different kind of techniques to do this regression task, but here we use lasso regression and subgroup discovery. So in this research, time series regression is applied to professional road cycling, and to do that we use data of a single GC rider of Team Jumbo-Visma, which is one of the best professional cycling teams in the world. So for the people who are not familiar with professional road cycling, a GC rider is a rider that focuses on stage races, which are races that last for multiple days. Then basically the goal of each stage, so the race on a certain day, is to gain time on the other competitors. So in this case we define a target variable as a time difference with respect to the final top 10 riders, because in this case the top 10 riders are also mainly GC riders and are basically, in this case we can compare our performance of our GC rider with his direct rivals. Moreover, we also have time series data, so for every stage we actually know that we have information for every second about the power the cyclist produced, also the speed, altitude, cadence. So this is actually monitored by using all kinds of sensors. So the cyclist actually uses his bike, which is equipped with all kinds of sensors. The goal of this research product is as follows. So given a stage profile, we want to predict the stage performance of a specific rider X relative to his rivals. So in this case a stage profile, so we start with a stage profile given to the left, which is basically the altitude as a function of distance covered with respect to the start of the race. We want to take certain steps and in the end predict the race outcome for this specific rider, which is defined as the time lost or actually gained in this stage. So this in the end can then be used for several purposes. For example, if a certain stage suits the rider, and also if you compare different stages of the same race, if actually this total race suits the rider. To predict this race outcome, we actually put the stage profile into a prediction model, and then the output is the number of seconds gained or lost for this rider. So to make this prediction model, we actually use the historical races of this rider X. So these historical races are then used in a two-step process to finally end up with a prediction model. So the first step is to use these stage profiles to extract a range of descriptive features that describe characteristics of this stage profile. So these features consist of two parts. So on the one hand we have a variable, which in this case is the altitude or the change in altitude. And the other one is that we use certain windows over which we aggregate those variables. So this, for example, could be the entire stage, and we also mainly focus on the final parts of the stage, as these are believed to be most relevant in the professional road cycling use case. So in this case, a feature is a combination of a variable and a window. So an example could be the maximum altitude in the last 10 minutes, but also the average slope over the entire stage. So if we have those variables, and we also know of course of the historical races what the race outcome for this specific rider was, we can build a regression model which actually finds the relationship between those features we constructed in step 1 and also the target variable, which is the number of seconds gained or lost. So in this case we use lasso regression and subgroup discoveries, but of course also other techniques can be used. So this is actually the first step of a pipeline, but actually the situation is a bit more involved. So what we also try to include is the physiological characteristics by introducing a so-called effective profile. So what do we mean by that? So in this effective profile, we use the convolution of the stage profile with a specified kernel k of t. So in this case, this k of t is an exponential decaying function, in which previous efforts are weighted with exponential decaying function. So to actually determine this effective profile, we use a model fitting procedure in which we first specify a certain weight parameter of this exponential decaying function, which is the kernel in our case. Then we calculate this convolution for this weight parameter, extract the features from the effective profile. Then we use those features and use regression, lasso regression in this case, and cross-validation to determine our model, and we determine also the accuracy of our predictions. So in the end, we repeat it for several weight parameters, and in the end, we choose our optimal values, which give us the most accurate predictions. So then this allows us to transform the stage profile into an effective profile. And here below you see an example of which is clear that this effective profile also includes the previous efforts. So this can be seen at the start of the second peak, which in the stage profile really goes to almost the same height as at the start of the race. But in the effective profile, this is way higher because it also takes into account that the rider already climbed this mountain. So this is the example of the effective profile, but to make the entire pipeline concrete, we also need to include another step, which is transforming the distance profile into a time profile, because the effective profile takes into account previous efforts and how actually our rider recovers from those efforts. But this actually depends on the time, which is actually between now and the previous effort, and not distance. So to make this pipeline complete, we also have to transform the distance profile into a time profile, and therefore we determined a so-called climb-descent model. So this climb-descent model basically gives a relationship between the slope of the terrain and the speed of a cyclist. So for that we also use the historical races of our rider, which resulted into more or less 2 million data points. So to determine this model, we used so-called polynomial regression, of which the details can be found in the research paper. Mainly what we did is we choose a certain degree of a polynomial, then use how accurate the model is, and then we optimized a polynomial degree to actually again get the most accurate model. The result is given in this figure. So on the left hand side between the dotted line we have the descent. So actually when the rider is going down a mountain, on the right then actually climbs a mountain. The solid line is actually a model and the shaded area is a confidence interval. So here we also see that this model is interesting by itself. For example, denoted by the red arrow here, we see that if the descents get larger and larger, at some point actually the speed goes down. It actually means that at lower speeds at larger descents. This is basically mainly because at very large descents our rider actually goes into hairpins where our rider is going really slow. So in the end this completes our pipeline and also our forecast. So what can we do now? So given a certain stage profile, which in this case is given by the solid line, we can calculate several things. So first of all we can determine the effective profile, which is denoted by the shaded area, which gives something about the heaviness that is experienced by our rider, which is already interesting for a professional cycling team. Moreover, you can use a climb-descent model to actually calculate or predict how much the rider will actually take or need to complete the stage. So this will also give us information about passage times of key points in the race. And finally, of course, we can also use a prediction model to predict a possible time gain or time loss for a specific rider. So for every stage profile, we can actually indicate if it is an opportunity to gain time, if we predict a certain time gain, but also maybe a possible hindrance if we predict certain time loss. So this actually brings me to the conclusion of our talk. So basically what we have done is we created a 3-stage pipeline to tackle time series regression in road cycling. So based on a stage profile, we can calculate several things, so which are all rider specific. So first of all, we can predict passage time for key points in the stage and also the duration of the entire stage. We can forecast also stage performance, so possible time loss or time gain. And we've also demonstrated that our approach provides valuable insights for a professional cycling team. Thank you for your attention.